Hey guys, how's it going? Here bringing you the last section of our Unit 6, which is dealing with exponential growth and decay, as it actually pertains to some real-world scenarios which we're going to actually model using both our growth and decay exponential functions. Alright, and one of the things that we actually look at in this section are the types of ways it's used in the real world, in terms of, for example, interest. That's one thing that you can see that exponential growth and decay actually take place. But let's go ahead and jump straight into it. So right away, we're going to go ahead and see that we have exponential growth here. So let's go ahead and type this. So when we're talking about growth, let's see what we have here. So we have this formula that has quite a few things in it. So we're going to actually break down exactly what all of those things mean. But before we even do that, I want you guys to take a quick look at, whoa, that's not a good color. Let's go back. How about green? There we go. Not too bad. All right. So let's talk about what the difference between both of those formulas are here. So growth and decay, the only thing that you should notice that is different in both of those is this. Here we have 1 minus R for decay, and here for growth we have 1 plus R. Okay, so that's one way to remember it, guys. When we're talking about growth, we usually look at increasing or adding, or what's called inflation, which we're going to talk about in a second. And when we're looking at decay, we're subtracting, we're going down, or we are actually decreasing or depreciating. So we're going to go ahead and cover a few of those keywords in a second. So let's go ahead and do that now. So between growth and decay, notice that the A of t, the P, the R, and the T are the same in both of those equations. So let's go ahead and write a few things here. So a few key vocabulary is initial amount. All right, we're going to be looking at initial amounts. We're looking at rate. We're looking at time. We're looking at total, or an ending amount. And notice I'm putting it across both of those, both all the way across that table, because that actually corresponds to both formulas. The only place where they differ is, like I said, on the plus and the minus, and we have a few keywords for that. So when we talk about growth, okay, we're talking about inflation or increasing. Okay, just like I talked about a second ago. So if you guys see those keywords, inflation, increasing, things like that, growing, okay, all those things will go and give you give you hints as to the fact that we actually have an exponential growth. Now, when we talk about exponential decay, we should be seeing things like decreasing, lowering. Okay, another word, the exact counterpart of inflation is not deflation, but rather depreciation. Okay, so if something depreciates in value, for example, it's going down in value. And usually you see that, for example, when you're talking about cars. After you buy a brand new car, after a certain amount of time, the value depreciates, and your car is no longer worth as much as it was when it was brand new. But again, remember, both of those formulas have pretty much all of the same variables. So let's go ahead and define what each of those things is. All right, so the first one. Sorry about that, guys. Totally sneezed all over my computer. But anyways, so this is a function right here. This is the function a of t. And this actually represents our ending value. Okay, so when we're calculating something, that we're finding our ending value or ending balance. Okay, so that is what a of t is. Our p is what's called our principal, or our initial amount. Or another word you might see is starting. If you hear the word starting anywhere in those word problems that we're about to see, you'll know that we're talking about the p value. All right, let's keep going. Next one you're going to see is t, and I'm sure you guys already have figured out what that one stands for. This one stands for time. Okay, usually in years. Not always, but for the most part, it will always be in years. Well, at least the way that these formulas are used, we usually have time in years. Okay, and then finally, R is actually our rate. Okay, and by the rate we mean percent. Okay, you'll usually hear that something increases at 3% inflation. Okay, so we're talking about something that we actually are going to have to turn into. Whoops, we're gonna have to turn this percent into a decimal. Okay, so when we calculate it and when we actually put it into the equation, we're gonna have to turn it into a decimal. And just FYI, when you do that, you're going to move the decimal 2 places to the left. Or in other words, you're dividing by 100. Okay, because if you already have percentage, that's like multiplied by 100, so you have to divide it by 100 in order to turn it into a decimal. Okay, so keep those few things in mind. I'm going to go ahead and highlight them here for you so we keep track of all of these. A of t is our ending balance or our ending value. T is our time. P is our initial amount. And finally, R is our rate or our percent. And remember, it has to be in decimal. Okay, enough talk. Let's go ahead and actually try out one of these problems. So let's first identify a few key things here that become apparent as soon as we start reading the problem. So let's see. It says teen spending is expected to inflate. So automatically right off the bat, I see a keyword there. Okay, it's it's inflating at 3.5% annually from 79.7 billion in 2006. Okay, so this looks like it's going to be an important number here. Now it says how much spending increased after 8 years. Okay, after 8 years. So I highlighted those. Now let's go ahead and see if we can figure out, first off, is this a growth or is this a decay? Well, hopefully you guys notice, just like I highlighted, this word right here. Inflation means growth, so we are going to use our growth equation. Right? All I did was copy that from the top. So go ahead and rewrite that. But again, we have too many variables here. We need to identify what each of those are. So we have an A of t, we have a p, we have an r, and we have a t. Okay, let's see which one of those things we were actually given. Well, it says teen spending is expected to inflate 3.5% annually. That's a percentage, which is a rate. Okay, that means we have our r. Well, as we said, we have to move the decimal twice to the left. So if it was, sorry about that, guys, if it was 3.5, then you have to move it 1, 2. So this is actually 0.035. Excuse me. So our rate is 0.35. I'm sorry, 0.035. Let's see what else we can find here. It says it's expected to inflate 3.5% annually from $79.7 billion in 2006. That's where we're starting, at 79.7. Again, which one is our starting value? That would be our P. So this is 79.7. And just keep that in mind that it's in billions of dollars. Okay. All right. We have that information now. Let's see if we can find our last bit of info here. It says, let's see, how much spending was increased after 8 years. And that, of course, is our time. So we have everything. The only thing we don't have is the A of t, but that's fine because we have everything else we should be able to solve here. So A of t we don't have, that's what we're looking for. Let's substitute everything else in now. So this is a 79.7, 1 plus my rate, which is 0.035, and then finally raised to the 8th power. Alright guys, go ahead and solve that and type that into your calculator. You should be able to type it in just as it is right now. If you don't have one of those graphing calculators, remember that you can always do this part first. Once you have that, raise it to the 8th power, okay, and then take that answer and then multiply it by 79.7. Okay, so let me take my calculator real quick. Let's go ahead and calculate this. All right, so 79.7 times parentheses 1 plus 0.035 raised to the 8th power equals, I got 104.95. So A of t, whoops, wrong pen. Try this again. A of t equals 104.95. And then what are we talking about here, guys? Well, A of t is our ending value, our ending balance. So this is in dollars, but remember our problem said we were in billions of dollars. So this is 104.95 billion dollars. And here is our final answer. Okay, so remember, read through the problem, identify whether it's growth or decay, choose the right equation, okay, and then identify all of the values that are given within the problem, and finally just substitute them back into the equation. So let's make sure you guys have that down. So what I'm going to do is actually go ahead and do number, let's see, I'm gonna actually skip number 2. I want you guys to try that one on your own. Let's go ahead and try number 3. Let's go ahead and scroll down. Alright, so it says, in 2011, a car valued at $6,500 depreciates, so right off the bat, I have a keyword there, okay, at a rate of 14.3% per year. Okay, so another key thing there is calculate the value of the car in 2014. Okay, well, let's see. First off, that keyword told us what kind of exponential growth is, or I'm sorry, what kind of exponential graph we're going to have, or what kind of exponential model we will have. So depreciates means growth or decay. Well, means decay. So that's the one we're going to use. So let's go ahead and rewrite that. So this would be A of t equals P1 minus R raised to the t. So again, I'm just using my depreciation formula from the very top of this page. Okay, so again, let's find out what things we do have. So off to the side here, I'm going to go ahead and write every single one of those variables. Well, I know we have a rate for sure. Okay, we had a 14.3, and remember, if it's 14.3%, what you have to do is move the decimal to the left twice. So this is really 0.143. All right. Next thing is our P, our principal, our starting value. It says a car valued at $6,500. So that's our starting value, $6,500. And that's what it was at in 2011 when it was purchased. Okay, so the question is, we're missing A of t and we're also missing t, but we can figure out one of those two. And hopefully you guys have already noticed that we go from the year 2011 to the year 2014. So you got to ask yourself, how many years have passed by? Well, 3 years have passed by. So I do have my t. All right, so finally, I just have to go ahead and substitute all of that back into my original equation. So why don't we go ahead and do that now. So this is A of P equals, now I have my P, which is 6,500, 1 minus my R, which is 0.143, and finally raised to the third power. All right, let's go ahead and type that into our calculator. So we should get, let's see, 6,500 times parentheses 1 minus 0.143. Be careful that you're using minus. Make sure you're using that. And then this is going to be raised to the third. I got 4,000. So let's write that here on the side. I got 4,091 and $25. Remember, we're talking about money here. So this is what I got for my final answer. Hopefully, after typing that into your calculator, you are getting the same thing. Okay. Once again, guys, if for some reason you don't have the capability of typing all that into the calculator like you can in the graphing calculators, then you should be able to still do this problem. And I'll show you how. So again, this is A of t. Solve this part first. Okay, so let's go ahead and continue solving this problem. So this would be 6,500. And then let's see, 1 minus 0.143 is it 0.857. Okay, now all I'm doing here is following our rules from PEMDAS, guys. I did parentheses. Next, I move to my exponent. So I have to raise this in my calculator. So you should be able to put that in your calculator. Let's see what we get. 1.857 raised to the third. Okay, you get some pretty big decimal here, but I'm actually just gonna round it to the nearest thousandth. So let me actually write this down. It would be A of P equals $6,500 times, remember between the 6,500 and the parentheses is a multiplication, times 0.629 is what I should have. And then finally go ahead and multiply that out. 6,500 times 0.629. You get a little bit of a discrepancy, and the only reason why is because we round it. Okay, so you get 4,088 and 50 cents. So there is a little bit of a discrepancy, guys. Maybe if you would have rounded to the nearest 4,000th, you would have gotten something a little bit closer to our actual value. Okay, so maybe right here, put one extra decimal, which would actually be 4. Let's see what actually that would give us. 0.6294 times 6,500. Much closer. That actually gives me 4,091.10. So very close to what we got here. But again, this you should be able to just type straight into your calculator right here, if you do have the graphing calculators. Actually, to be honest, I think even if you have the scientific calculators, you should be able to type that in. Just make sure you're using your parentheses, guys. Okay? Alright, guys, so I apologize for dragging that problem longer than I probably should have, but I do want to make sure I show everyone who might not have access to those graphing calculators a different way of doing this. Okay, so what I want you guys to try out right now is problem numbers. Let's see, we still have about 3 more to go. 4 more to go. Why don't you guys go ahead and try out number 2, and then we will go ahead and go over it and do maybe one more of the problems on these notes. So go ahead and try those out, guys. All right, let's go ahead and take a quick look at problem number 2. So let's read through it, find out what kind of exponential equation I'm going to use, whether growth or decay, and then finally start substituting values in. All right. So it says Daniel's print shop purchased a new printer for $35,000 $1,000. So that's what I initially purchased, or Daniel initially purchased it for. So as you go back to your terms from up top, initial values right here, guys, that's your P. I'm going to go ahead and put a P there. Okay, let's keep going. Each year it depreciates. Okay, it depreciates. So what kind of exponential will it be? Oops, sorry about that. It's going to be a decay. I'm going to have to use the decay exponential equation. And then it says each year it depreciates at a rate of 5%. So that's my R. My R. It says what will its approximate value be at the end of the 4th year? So how much time passed is my T. So I actually have pretty much all I need. So again, off to the side, let's go ahead and start writing down what we need. Well, this is a decay, so I'm going to use A of T equals P 1 minus R raised to the T. Off to the side, I'm going to write down every single value I have in my problem. All right, so I know my P, that's $35,000. Okay, my rate is 5%, but remember, if your decimal is here, you have to move it 1, 2 to the left. So this is actually 0.05, all right? And then finally my T, well, we're talking about after the 4th year, or at the end of the 4th year, so we're looking at a T of 4. Okay, I think we have everything we need here. So let's go ahead and start substituting. So this is going to be A of T equals, our P is 35,000, 1 minus R, which is 5, and finally raised to T, which is 4. Okay, so type that all into your calculator, guys. I'm going to go ahead and do the same thing, and we will compare answers. So 35,000 times parentheses 1 minus 0.05 raised to the to the 4th actually, and I got, and again, consider we're talking about money here, guys, so you shouldn't need to round more than to the nearest hundredth. So let's go ahead and see what we get. I got A of P equals $28,507.72. And notice how I added my units. You need to add your units anytime. Excuse me, anytime you go ahead and calculate any of these problems. All right, so $28,507.72. That's how much the printer is worth after the 4th year it was purchased. So it went down quite a bit of money here. We're looking at close to $6,500. So yeah, these are real world scenarios, guys. I mean, this happens, like I said, with my earlier example with cars. It happens all the time. They usually depreciate at a certain rate. But that's not always the case. Sometimes they actually start growing. It's an actual growth of value. For example, like classic cars, even the longer they're available, or the older they are, sometimes they grow in value. So those are just a few different examples, guys. So now you know exactly what these kinds of models will help us find. Okay, I think I'm going to go ahead and go over number 5 with you guys, and you should be able to take care of 4 and 6. So let's go ahead and go over those, and then you guys will try the rest on your own. So it says, example number 5, an adult takes 400 milligrams of ibuprofen. Okay, each hour, each hour the amount of ibuprofen in the person's system decreases by about 29%. How much ibuprofen is left after 6 hours? Okay, so, oh, I forgot to highlight that one. So let's go ahead and talk about whether this is depreciation or, whether it's growth or whether it's decay. Well, decreasing, that word decreasing there is a key word. for decay. So once again, we have a decay type of problem here, so we know we're going to have to use our decay formula. Remember, this is when you have a minus here. Okay, so let's go ahead and identify the rest of our values. So A of t, P, R, and T. Notice, guys, I keep writing A of t even though we are always pretty much in these problems looking for A of t. Well, that's not always the case, guys. So I would still write it down. All four of those things are potential values given within the problem. So I always write them down, and whichever one I didn't get in the problem, I know that's the one I have to look for. Okay, so an adult takes 400 milligrams of ibuprofen. That's the initial amount that they were taken. Okay, so that's my initial amount. That's my P. So 400 milligrams is the initial amount of milligrams of ibuprofen before it starts decreasing. All right, and then now we're looking at rate. Well, I see that right here. It's 29%, but 29, if I move the decimal to the left, is actually 0.29. Remember, guys, another way of doing this is just taking your 29, the percent, and dividing it by 100. Okay, type that into your calculator, and you should get 0.29. This is how you'll actually see it on your calculator. Okay. All right. Let's go ahead and see what else we got here. We are also given that it's asking rather how much ibuprofen is left after 6 hours. So that is our time. Whoops, wrong thing here. So it's 6 years is. I'm sorry, sorry, not 6 years. 6 hours is our time. Okay. Now the only thing that I don't have here is A of t, so I know that's definitely what I'm looking for. Let's write A of t equals, substitute 1 minus 0.29 raised to the 6th. Once again, I'm going to type that all into my calculator and see what I get. So 400 times 1 minus 0.29 raised to the 6th power. And if you guys have similar answers to what I have, this is what you should have. You should get A of t equals 51.2. I'm going to round it to the nearest hundredth because we're not talking about money here, but we can still round to the nearest hundredth. 51.24, and then what are we talking about here? We're talking about milligrams. So no longer money, but we are talking about milligrams. Okay, so that is my ending value. After depreciating for about 6 hours, my ending value, or the amount left in that person's system, would be 51.24 milligrams of ibuprofen. Okay. All right, guys. Kind of thinks that we did more decay problems than growth problems, but honestly, it honestly doesn't matter. The only difference between both of them is that within the problem, it'll say increasing, inflation, things like that. And because if it does say that, you definitely have to use the other equation, which would be P times 1 plus R raised to the T. Okay, but I think as of now we have done enough problems for you guys to finish the rest of the notes. You should only have 2 more problems to complete, and then you can move on to the homework. So I think I'm gonna go ahead and cut the video short here. Actually not too short, it's about 30 minutes. So I'm gonna go ahead and cut this off now, and you guys should be able to complete the rest of it. Okay. All right, guys. Last video for Unit 6 will be tomorrow, or the one I record next. That will be day 2 of 6.4. So we're going to actually be talking about compounding. All right. So I will talk to you guys soon, and I will see you guys during that video. Take it easy. Bye.